Today, we're diving into the fascinating world of electromagnetic induction. This phenomenon is not just a cornerstone of physics, but also a driving force behind much of our modern technology. From the power grids that light up our cities to the electric motors in our appliances, electromagnetic induction is at the heart of it all. All right, let's start with some basic concepts. First, we have magnetic fields. These are regions around a magnetic material where the force of magnetism acts. Next, electric currents, which are flows of electric charge. Conductors are materials that allow electric currents to flow through them easily. And finally, induction, which is the process of generating an electric current from a changing magnetic field. Now, let's talk about Faraday's law of induction. This law states that the induced voltage in a circuit is proportional to the rate of change of the magnetic flux through the circuit. In simpler terms, if you change the magnetic environment of a coil of wire, you will induce a voltage in that coil. It's a fundamental principle that underpins much of electromagnetism. So, how does induction work? Imagine a magnetic field moving through a conductor. As the magnetic field changes, it pushes electrons in the conductor, creating an electric current. This is induction in action. It's this movement of magnetic fields and their interaction with conductors that makes so many of our technologies possible, from transformers to electric generators. Lenz's law, named after the physicist Heinrich Lenz, states that the direction of the induced current will be such that it opposes the change in magnetic flux that produced it. This essentially means that the induced current creates a magnetic field that counteracts the original change. This principle is crucial for understanding the behavior of circuits and magnetic fields in various applications. Now let's explore some real-world applications of these principles. Generators, for instance, convert mechanical energy into electrical energy using electromagnetic induction. Transformers, on the other hand, transfer electrical energy between circuits through inductively coupled conductors. And then there are induction cooktops, which heat pots and pans directly through electromagnetic fields, offering a more efficient cooking method. These are just a few examples of how electromagnetic induction is utilized in our daily lives. So, how do these applications impact our daily lives? Well, generators are essential for producing the electricity that powers our homes and businesses. Transformers ensure that this electricity can be efficiently transmitted over long distances. And induction cooktops provide a faster, safer, and more energy-efficient way to cook. All these innovations, driven by the principles of electromagnetic induction, play a significant role in making our modern lives more convenient and efficient. Experiments and demonstrations can really bring the concept of electromagnetic induction to life. For instance, you can try a simple experiment using a coil of wire and a magnet. Just move the magnet in and out of the coil and observe how a current is induced in the wire. This is a great way to see Faraday's law in action right in front of your eyes. Another easy experiment involves using a small motor or a hand-cranked generator to show how mechanical energy can be converted into electrical energy. These hands-on activities are perfect for classrooms or even at home. When conducting these experiments, it's important to keep safety in mind. Always use insulated wires and handle magnets with care to avoid pinching your fingers. If you're using electrical components, make sure they are properly rated for the voltages and currents you are working with. As for expected outcomes, you should see a measurable current in the wire when the magnet moves through the coil. This demonstrates the fundamental principle of electromagnetic induction. There are a few common misconceptions about electromagnetic induction that are worth addressing. One major misunderstanding is confusing induction with conduction. Induction involves generating an electric current through a changing magnetic field, while conduction is simply the flow of electric current through a material. Another misconception is thinking that a stationary magnet can induce a current in a stationary coil. In reality, there must be relative motion between the magnet and the coil to induce a current. To wrap things up, we've covered the basics of electromagnetic induction, demonstrated some simple experiments, and clarified common misconceptions. We encourage you to explore more about this fascinating topic and its numerous applications in the real world. Whether it's in power generation transformers or even your everyday electronic devices, electromagnetic induction plays a crucial role in modern technology.